Let's start a discussion about special theory of relativity, which was given by the famous scientist Einstein, and we will derive the most famous equation in physics, probably equal to mc square. Now, the special theory of relativity is applicable only for inertial reference frames. What are the inertial reference frames? The reference frames which are moving with a constant velocity v or which are not moving at all, that means they are at rest, are called inertial reference frame. Reference frames with acceleration is not allowed at all. That's why inertial frames moving in circular orbits are not allowed, because for them a centripetal acceleration is involved, and whenever there is an acceleration we need to apply general theory of relativity. Now, for example, we take two spaceships, two reference frames. With respect to me, I am standing on earth. For me, s is at rest and s dash is moving with respect to s with a velocity v. Now, we can only say that s dash and s have a combined velocity or relative velocity v. So, now let us consider two clocks associated with the two reference frames. They are synchronized and they will synchronize forever. No, this is not true. They will not synchronize forever. This is just imagination. Let's hope so. So these are my frames, S and S dash. Suppose S has an antenna, S has a wire and S dash has an antenna. Whenever S dash passes S, the observer at S will hear a tickling sound, a beep sound. Now, after a short interval of time, a flashlight occurs somewhere. Now, what is the coordinate of this somewhere? According to S, this flashlight has occurred at a position x at time t. According to S dash, it has occurred at a position x dash and at time t dash. Both are true. Both manifestations, both illustrations are equally good. We can't deny one or the other. Now, what is x? X is evidently x dash, that is distance between the occurrence of flashlight and the coordinate of S dash at a particular time t dash, and plus the distance between S and S dash. So, x is equal to this difference of S dash plus this distance x dash. So, x is equal to x dash plus separation distance between S and S dash. Here just I have written that in expression, because in this time S dash is moving with respect to S and with a velocity v, it has already traveled a distance vt dash in the meantime. So, this is my equation 1, and this is my equation 2, because x dash is nothing but the entire x minus the separation distance between S and S dash. Before going into special theory of relativity in detail, this experiment of Michelson and Morley is worth mentioning. Now, what they tried to measure is they wanted to measure the speed of our planet Earth with respect to a fixed point in space, and they called the fixed point as ether, but later it was found that there was no ether. Then a second thing, they thought that the speed of light is not constant and it varies as the speed of Earth is varied with respect to the fixed position, which is ether. So, as the speed of Earth is different for different fixed positions, speed of light is also varying. That is also wrong. We know that the speed of light is universal, constant. Now let me cite this thing, the little example. A train is going rightwards with a speed of 30 miles per hour. A person who has boarded inside the train has thrown a ball rightwards with a speed of 20 miles per hour. So what is the speed of ball with respect to me? There should be this sign. Now I am standing on the platform. With respect to me, this train is going with the man inside. So with respect to me, the ball is going simple, 30 plus 20, it's 50 miles per hour in the direction in which the train is moving, that is rightwards. Now what if the person throws the ball leftwards? Okay, so what is the speed of the ball with respect to me? The speed of the ball is 30 minus 20, that is 10 miles per hour. But the direction is still in the direction of propagation of the train, that is rightward. So in both the cases, the ball is going in the rightward direction. Here with the speed of 50 miles per hour, here with the speed of 10 miles per hour. That is quite simple, quite obvious. Now what if the person switches on a torch? So person switches on a torch, a light is coming, a flashlight is coming through the torch. Light is going with the velocity c. C has universal velocity 3 to 10 to the power 8 meter per second. But what is the speed of light with respect to me standing on the platform? It is c. It is not c plus 30. That is 30 is the direction of 30 is the velocity of the train itself. Similarly, if the person switches on the light in the leftward direction, with taking the torch and turning this way, and then switches on the torch, then the light is moving leftward to the train is moving in this direction, even then the speed is c, not c minus 30. So we have learned that the speed of light is constant and it is independent of the motion of the source and the observer. So speed of light is c, and that is constant, 3 to 10 to the power 8 meter per second, and it is independent of the speed of source or the observer, and that is the maximum speed with which an information can travel. So the calculation of this velocity or speed of light is very much different from the calculation of the speed of the ball. So what was wrong there? Probably the experiment, maybe there will be a would be a faulty experiment, because speed is distance by time. Perhaps people have measured distance wrong, or perhaps they measured the time wrong because of the clocks they took, maybe faulty. Now we are returning to our own S and S dash frames, our spaceships. So for this flashlight, S will tell that the flashlight has occurred at position x in time t. S dash will tell the flashlight has occurred at position x dash time t dash. Both the illustrations are correct, and according to S, the speed of light c is x by t, distance by time. According to S dash, it is c equal to x dash by t dash. Now evidently we can see here that x dash are quite different. So t dash must be different. So I have two frames, S dash, and everyone measures in its own frame the velocity of or the speed of light, and everyone thinks he is the legend and the other is wrong. Everyone thinks he is correct, other is wrong. Let's have this factor, the wrong factor, be gamma. So S dash thinks that there is a gamma amount of error in measurement of x which was done by observer in S frame. So S prime observer thinks that S is wrong, and wrong by an amount of gamma. So according to him, X is gamma times X dash plus X prime plus ut prime, and according to S dash is wrong. So according to S, the measurement of S dash, which is X dash, is wrong by a factor of gamma. So X dash equal to gamma times X minus ut. Now what is gamma? Now we multiply X into X dash. If we multiply X into X dash, just multiply this left hand side and right hand side. In the left hand side I have X dash, then gamma square, these two terms. Then just multiply X prime plus ut prime X minus X prime ut minus u square t prime, and I have substituted t equal to distance by velocity, speed, that is t equal to x by c in frame S, and t dash equal to x dash x prime by c in frame S dash. So just I have put the values for t and t dash, and we got this. Then I will divide both sides by x prime. So if I divided both sides by x prime, then we have 1 in the left hand side, and the right hand side we are left with gamma square 1 plus u by c minus u by c minus u square by c square, and we got gamma square equal to 1 by 1 minus u square by c square, and gamma is this one. This is equation 3. This is called Lorentz transform. We will apply this, but first apply it here. So putting in the expression of x dash the value of gamma, we got equation 4 and 5 respectively. But these two equations are valid only if u is comparable to the speed of light. If u is very small compared to the speed of light, that means u square is extremely smaller compared to c square, because a small quantity becomes smaller when it is squared. So it's we can neglect this fraction, and the denominator turns out to be just 1, and x is this much. So we are in the Newtonian mechanics then. So gamma is valid only if u approaches c, and then when u approaches c, the cases become relativistic. Now from equation 4 we derive another equation. We have x dash equal to gamma x minus ut. We put again t equal to x by c, and then we divide by c both sides of the equation, and we got t dash, that is the time measured in the S dash frame, which is equal to gamma t minus ux by c square. This is equation 6. So from equation 5 we have derived this equation 6. This is expression of the coordinate in S dash. This is expression for time in S dash. Now this is x equal to gamma x dash plus ut dash t prime. So x equal to x prime, and again we are substituting x dash over c for t prime. So we have dividing both sides by c. We have x by c equal to x prime by c plus ux prime by c square multiplied by the gamma factor. So here we have the expression of the time as measured in the S frame. So this is the expression of coordinate measured in the S frame. From this we have derived the expression of time in the S frame. And what is important is all these 4 equations. So far we have derived 4 equations, and all this equation tells us that the observations made in the frames S and S dash are same unless we approach the speed u tends to c, that is unless the relative speed between s and s dash approaches the speed of light, these four equations are not valid and not relevant. Now, time measured should be different from different reference frames. What does that mean? This equation suggests that in one frame the time measured is t and in another frame it is t prime. Suppose in a spaceship 2 mirrors are kept and light is allowed to go from this mirror to this mirror, and then again it makes a return journey from this one to this one, and the distance between the two mirrors is 1 meter. Now, as the velocity of light is 3 × 10⁸ meter per second, total distance traveled by light is 2 meter. So in 1 second the light completes 1.5 × 10⁸ cycles of to and fro journeys, and there is one counter. So once light gets back to this mirror, this counter ticks. So how many times the counter, that is the clock, ticks, that records the number of time the light actually completes its journey. So this is how we are measuring the time. Now suppose this spaceship is moving and this entire arrangement is kept in this spaceship. It is moving as a whole with a velocity v. So this mirror arrangement is also moving with speed v, and here I am stationary, I am in another spaceship. So I am seeing that this mirror is going like this. So for me, the journey of light will not be just vertical to and fro motion. When the light pulse starts journey from down mirror and it reaches the top mirror, but by this time the spaceship as a whole moves by a certain distance. So for me, the light is making a horizontal upward journey instead of a vertical upward journey. And when the light pulse again returns back to the lower mirror, then again by this time interval, the spaceship has moved from this position to this position. So instead of making just a vertical journey from top to the bottom mirror like this, for me, the light is making a downward horizontal transition. So instead of moving vertically, I am seeing light pulse going upward, making an angle, and same thing occurs when the light pulse again comes back to the down mirror. Again it's making an angle. So here this distance between the two mirror is 1 meter, but for me the light is traveling from this to this way. It is traveling this much distance and then again it is returning back to the lower mirror. So for me, light is traveling from here to here and then here to here instead of the vertical journey. So for me, the time taken by light is greater because it is making a longer route. But we know that the time measured by the clocks should be lesser, because the relationship looks like this. It is t minus ux by c square. So here that means that moving clocks run slow, which means that the time taken by light, according to me, is actually longer than what I think, and hence I will infer this as any moving clock runs slower. That is, time intervals elapsing in clocks which are moving are greater than the clocks are in my hands. So, according to S, the clock which is attached to S dash, the reference frame which is moving with speed v with respect to S, and the clock in S dash is moving, and that moving clock is running slowly according to S. S dash will infer the same. He will say that the clock in S will be running slowly, but it is not possible to measure that. But if he wants to verify that this clock is actually running slowly or not, then he needs to land up on S. That is not possible, because when he is landing up on S, he is changing velocity, he is having a retardation, that is a negative acceleration, which cannot be taken into account in special theory of relativity. That is a general theory of relativity thing. But experiments on very high speed aircrafts and with very precise clocks, it can be shown that moving time is actually slow. Moving clock is actually running slow. Now, what if S and S dash observe particles? In the reference frame S, a particle is here, suppose, and it is moving with speed v. S measure the distance travelled by the particle, which is x, in time t, that is according to S, and the same speed measured by S dash also. The relative velocity between S dash and S is u, and speed of the particle according to S dash is w equal to x dash by t dash. X dash is distance travelled by observer in S dash. T dash is time taken into account by S dash, and from this we know velocity equal to distance by time, and in place of x dash we can put x minus ut into gamma, and in place of t dash we can put t minus ux pi c square into gamma. And after some algebra, after doing some very simple algebra kind of thing, we have arrived into equation 8. So, this is the w is speed of the particle measured according to S dash, which involves the relative velocity u between S and S dash, and velocity of the particle itself v, which is measured by the S observer. And doing the same algebra, we can deduce this relation also, and this is relation 8. Now, what if w is equal to c? What if the particle is actually a photon, light? Suppose in S frame an event occurs. According to S, the event occurs at time t, capital T. But S says I am not moving, so displacement x is 0 for him. Now, what will be this time calculated in the S dash S prime frame observer? S prime is moving with speed v with respect to S. Now, according to S prime, the time calculated for that particular event is t minus ux by c square into gamma. Gamma is root over 1 minus u square by c square. Now, according to S, x is 0, but as S is not moving at all according to him. So, if we put x equal to 0, we got t prime equal to t by root over 1 minus u square by c square, and from equation 11, it is quite evident that this time interval is certainly greater than the time t. This is actually time dilation, which means the time interval registered in the moving clock is longer than the time interval registered in a stationary clock. All the moving clocks with respect to me are running slow, and the clock is in my hand is giving the actual time for me. Let's discuss length contraction. Suppose I am going to measure a length L. I am in this frame S, and this S is moving with the speed u with respect to S dash, S prime. In S prime, the length measured is L prime. In S, the length measured is L. Now, as the length of any rod has to be measured simultaneously, length is actually the distance between the two terminal points, and these two terminal points has to be measured simultaneously. It is not like that it is moving and I am measuring the coordinate of this point and going somewhere and then having my lunch and then again coming back and then again measuring the coordinate of this terminal point. This does not make any sense. So t should be equal to 0 because the two terminal point coordinates of the two terminal points has to be measured simultaneously, and the difference of the two coordinates point will give me the length of that rod. So if we think about this relation, this coming from this one, this x prime equal to x minus ut root over 1 minus u square by c square. We have derived this earlier, and as t is equal to 0, so this comes to be x divided by root over 1 minus u square by c square, and x is here L and L prime for S prime. So according to S prime, L prime is L by root over 1 minus u square by c square. Hence L is equal to L prime into root over 1 minus u square by c square. This is equation 13, this is equation 12. Now from this relation, it is quite evident that the moving rod, which is this one, must be shorter in its length because of this root over 1 minus u square by c square factor. So if we measure the length of the moving rod, it appears for me to be shorter. So anything which is moving with respect to me appears to me as shorter, except the rod which is I am holding in my hand. Now let's discuss causality. Is it possible that the effect occurs before the cause itself? Let us consider two events, 1 and 2. If we think of the two stars, one is A and the other is B. This is Earth, I am standing here. This A star is 8 light years away from me. This B star is 2 light years away from me. An event occurred at this A star 4 light years ago. And here at the B star, an event occurs, say 1 light year or 2 light years ago, for example. Naturally, this occurs. Next, we will discuss causality. Is it possible to see the effect before the cause? Suppose there are two events, event 1 and event 2. For example, I am standing on Earth and there are two stars, one is A and the other is B. The star A is 8 light years away from the Earth and the star B is 2 light years away from the Earth. A light pulse started its journey before 4 light years from star A, and another light pulse started its journey before 2 light years from the star B. What will reach me? Which light pulse will reach me first? The light pulse from B will reach me first because it is closer to me. In spite of the fact that the light pulse at A has occurred before the light pulse of B, but as A is closer to me, so now after 4 light years, the light pulse from A has reached only half away, and it still yet to reach Earth. I will see it after 4 light years. Now what I am receiving is the light pulse emitted from the star B. But what if one event causes the other to happen? Suppose an event occurs at A and that event then reaches to me. I am standing at O and it reaches also at B. Whenever it reaches B, then it triggers another event at B. Then is it possible that I will see the information of the event occurring at B before the event at A? No, it is not possible, because A has caused this event at B to occur. Now we will be discussing about simultaneity. Simultaneous means occurring at same time. Let me cite an example. Suppose I am standing roadside and I am seeing 2 cars collide. That is occurring at a certain time t and at a certain position x in my reference frame. Now, is it possible that somewhere in the universe, anywhere in the universe, is seeing the same event occurring at the same time and at the same place, and he is observing that the 2 cars missed each other? It is not possible. So the event, so far we are familiar with XYZ t. XYZ correspond to position, space, and t correspond to time. Here just a change of notation, and as I am writing all the coordinates together to make the 4 vector x, so just in order to make the dimensions of all the components of the 4 vector capital X same, I will write instead of t x0, where x0 equal to ct. C is the speed, t is the time, and speed into time gives me position or distance. So x0, x, y, z all are of same dimension. X, y, z are measure of space, x0 is measure of time. But here I will use these notations because in higher dimensions we may be running out of alphabets, like x, y, z are done here. Then I need small w, small t, etc., etc. But we won't be running out of numbers. We can use as many numbers as we want. So instead of xyz, I am writing it as x1, x2, x3. So x1, x2, x3 are space, x0 is measure of time, and x0 equal to ct. I will use this x0 equal to ct. Let's put another substitution, u by c equal to beta, for example. Before making this x1 prime equal to x1 minus this stuff, I just would like to remind you this equation. We know that x prime equal to x minus ut by root over 1 minus u square by c square, and u square by c square is nothing but beta square. So x prime is equal to x minus ut by root over 1 minus beta square, and I am just multiplying and dividing with c, speed of light, which gives me u by c. In place of u by c I will put beta, and in place of ct I will put x0. So I am here x prime equal to x minus beta dot x0 dot, actually it's beta x0, divided by root over 1 minus beta square. And instead of writing just x, because instead of writing x I am using x1, so here it is x1 prime equal to x1 minus beta x0 and divided by root over 1 minus beta square, because instead of time we are using x0 onwards. So here are two changes of notations. X becomes x1, t becomes x0 by c. So my new equation is x1 prime equal to x1 minus beta x0 by root over 1 minus beta square. This is equation 14. Again the same thing can be written for this time equation t prime. So for the time equation t prime, I am again putting x1 instead of x and just write it as u by c into x1 by c. Gamma is 1 by root over u square by c square. So here I am multiplying and dividing by c. So it's ct by c minus u x1 u by c into x1 by c. And here if I take this c, this 1 by c out like this, I am left with the expression in the parenthesis, and we know ct dash equal to x0 dash because x0 equal to ct. So the equation is x0 prime equal to x0 minus beta x1 by root over 1 minus beta square. So here is the entire derivation. And this is equation 15, and for simplicity we are dealing only with the time coordinate and one dimensional space coordinate, that is x1 and x0. Now let us define a new quantity s square, which is equal to x0 prime square minus x1 prime square. I will use equation 14 and 15 both, and I will put instead of x0 prime x0 minus beta x1 by root over 1 minus beta square, and as it is x0 prime square, so the square is for that. Instead of x1 I put x1 minus beta x0 by root over 1 minus beta square, and then this algebra I'm just writing using the a minus b whole square term. Because of this square, the square root is gone and I am left with 1 minus beta square in the denominator only. And after some algebra I have arrived at this situation. If I take 1 minus beta square common, so I have x0 square minus x1 square. I have started with x0 prime square minus x1 prime square. I have found that this is equal to x0 square minus x1 square. So s square is invariant of the reference frame, because x0, x1 are the coordinates in S frame and x0 prime, x1 prime are the coordinates measured in S prime frame. This invariance is my equation 16. And what is this quantity S? We have defined S square equal to x naught square minus x1 square. Now x0 is equal to ct, so this is c square t square minus x1 square. Dividing both sides by ct square, I will get on the left hand side s square by c square t square, right hand side 1 minus x1 square by ct whole square. So s square is this much. If we want s, then I will have s equal to ct root over 1 minus x1 square by ct whole square. Again we know that x1 by t equal to v, because position by time, distance by time equal to the speed. So this is ct root over 1 minus v square by c square. So I have s by c equal to t into root over 1 minus v square by c square. You may call this equation 17 or you may call this equation 17. I will take this one as equation 17. Now, deriving from equation 17, I will have s by c. Actually, I have already deduced the two lines over there. So s by c equal to t into root over 1 minus v square by c square. I will define this quantity tau as proper time. As this is distance by speed, so dimension of this s by c quantities must be time. This is a special type of time. This is time in the clock which is kept in my hand. Except this clock, every other clock will appear to me, every other clock which are moving appear to me slower. So proper time is the time which is given by my clock, and all the other clocks, moving other clocks, are running slow. If we think about particles, then the proper time refers to the clock traveling with that particular particle. Now let's define 4 momentum vector. I have defined 4 vector x with 1 time and 3 space coordinates. Now let me define the 4 momentum vector. So p is equal to mv, so I will write m, and instead of v I have to write position by time. This is velocity, speed. So this is the time part of the 4 vector, and these are the spatial parts. So this is the expression of the 4 momentum vector. First element of this 4 momentum vector is mx0 by tau. Second element is mx1 by tau. Third element, fourth element. But for simplicity, I will stick into one dimension and I will take these two terms only. So for the time being, I am taking p equal to mx0 by tau and spatial term x1 by tau. If I put x0 equal to ct in the first element, I will have mc. Now according to this relation, t by tau is 1 by root over 1 minus v square by c square. So here it is mc t by tau is 1 by root over v square minus c square. Similarly for p1, which is the second element, I will have this term. Now I will apply this binomial expansion, the famous expansion in algebra, which tells me that if I have a quantity 1 plus x whole to the power n, then I can expand it like this. I'll stick to the first two terms because I assume that all the other terms onwards are slower, so there is no point of taking those terms into account. If we apply this binomial expression to 1 by root over 1 minus v square by c square, so this as power, this is n equal to minus half. So my expansion will look like 1 plus half v square by c square. I will put, instead of 1 by root over 1 minus v square by c square, this whole thing. So my first element then becomes, my first element for momentum was p1, actually this is the second element. It is p1 equal to mx1 by t into root over 1 minus v square by c square. Now x1 by t is nothing but v. So I have mv 1 by root over v square minus c square. Using this expansion here, my p1 is mv plus half mv cube by c square. This is ordinary momentum. I am familiar with this. We all familiar with this. Momentum equal to mass into velocity. What is this term? This must be some correction, relativistic correction. This comes only when the speed of the object approaches the speed of the light. If we are in a domain such that v is very small compared to c, that is the speed of the object is very small compared to c, then this v cube must be extremely smaller compared to c square. This is c square. This is again a very bigger term. So I can neglect this term and I will remain only with p1 equal to mv. And my time term, which was the first element, which was p0 equal to mc by root over 1 minus v square by c square, again taking into account the binomial expansion, I got p0 equal to this much. Now multiplying the whole expression with c, I will have p0 c in the left hand side, right hand side I will have mc square plus half mv square. Now what is this? This is familiar kinetic energy. This is energy. This is energy. This has to be energy. But what is this? This term says that even when the kinetic energy is 0, that is the particle is resting, v is equal to 0. The particle or the object must have some rest energy, which is mc square. And this is the famous Einstein E equal to mc square. We have seen already that x0 square minus x1 square is actually an invariant quantity. Let's see what happens if we do p0 square minus p1 square. Now according to equations 18 and 19, p0 is mc gamma. Gamma is 1 by root over 1 minus v square by c square. P0 is the time component of the 4 momentum. P1 is the space component of the 4 momentum. So using equations 18 and 19, we have written it P0 square minus P1 square equal to mc gamma whole square minus mv gamma whole square. So we have to do some algebra. M gamma square is common, so it's c square minus v square. Taken this c square out, we are left with 1 minus v square by c square in the parenthesis. So the expression looks like m square c square by 1 minus v square by c square multiplied by 1 minus v square by c square. So this cancel out. From p0 square minus p1 square, we are getting that that is equal to m square c square. Now m square c square is another constant, which means p0 square minus p1 square is also constant. What does that mean? That does mean that p0 square minus p1 square is actually independent. of the fact that in which frame I am calculating P0 square minus P1 square. So it is independent of the reference frame. Now we have used equation 21 and written total energy E equal to P0C, which is equal to mc square plus half mv square, and from equation 22 we know that P0 square minus P1 square equal to m square c square. So using these two equations we came to this expression. So I am multiplying it with c square. Here I have just made a change of notation. Instead of P1 I have written P, just to denote that it considers the ordinary momentum mv. So here is my equation 23, E square equal to P square c square plus m square c to the power 4. Again we have derived E equal to mc square from this relation. This tells that if the particle has zero momentum, that is it is at rest, so this makes P equal to 0, which makes Pc equal to 0, and I am left with E square equal to m square c square, and I get E equal to mc square.